Hello everyone. In this next module, we are going to be learning about topology optimization and how that can help us make a better design. So for topology optimization, it's very similar to the last one that we did. We're going to go up here and click on the simulation tab. We're going to create a new study. And instead of a static simulation this time, we're going to choose a topology study. Okay, so we'll just allow this name to be Topology Study 1, and we'll click OK. And now down here we see a new tab that says Topology Study 1, the name of our simulation. So that looks good. Very similar to the last simulations that we did, we're going to have to apply all of our fixed positions and all of our external loadings. So let's apply a fixed geometry on the left-hand side of the beam, just like we did last time. Over here on the right side of the beam with the mountings, we're going to have to add some external loads. So we'll right click there and we will add some forces. The forces we're going to add on the tops of these cylinders. There we go. And now that's the wrong direction. We want to choose the direction, so we'll choose the direction of this axis. And let's make it 1 Newton. I think that's what we used the last time. And that will be total 1 Newton. Okay, other loads that we have to add. We have 4 reaction torques that we have to add. So we'll do that the same way we did it last time. Click on the inside cylinder. And this is wrong, so you're going to have to delete that or clear it and also choose the inside of the cylinder. Should say the same face number for each one. And just like last time, we'll make these 0.05 Newton meters each, and we have to do these individually. So there was the first one. We'll add the next 3 next. .05 Newton meters. Okay, on to number 3. And that one's done. And the last one. Okay, perfect. So we've got our 4 reaction torques. Now here's where it gets a little bit different. This time, the next thing on our to-do list is defining the goals and the constraints of the project. So if we right click it here, there's 3 different fundamental goals for how we can do our optimization study. So for a flying project, a drone project, like this is a drone arm, probably what we want to do is minimize the mass. That may not always be the case. Sometimes we may want to minimize the maximum displacement. Sometimes we might want to make the best stiffness to weight ratio. So in this case, we're going to do minimize mass. Okay, and here's our opportunity to add any constraints that our system may have. We could also say that, well, we want to minimize the mass, but if we check this box, we'll add a displacement constraint, and maybe we have to say that it can't displace more than 1 millimeter for some kind of geometrical reason. Maybe the aim of the propeller is off then, or something like that. So if we wanted to add that, we could. If we wanted to say there was a mass constraint, like it couldn't be any more than 1 kilogram, I don't know. Or this is a frequency constraint, and frequency is related to the mode of the free vibration, so we can also do that. We can also do it based on stress or factor of safety constraint. So in our case, that's what we want to use. So we're going to say it's a stress constraint, and we are going to say that we don't want any portion of this beam to experience more than 75% of the maximum yield strength value for balsa wood. Okay, so we can do a green check mark there. So that set up our goals and our constraints. If we had any manufacturing controls, like if there was some region that had to stay in there, maybe because it makes contact with another part, maybe there's a a certain thickness that we have to maintain. Maybe we're cutting this out of a 6mm sheet of balsa wood, so we would say it has to stay 6mm. So there's different ways that you can specify manufacturing constraints on there too. And now last is mesh. So just like we did last time, we're going to create a mesh. Now this is where it gets really important, because topology optimization, basically what it does is it's going to run a constraint, it's going to run a simulation, and it's going to look for the areas that have extremely low stress. So if it has low stress, basically what the simulation is going to think is that piece of material doesn't need to be there. So it's going to remove it, because we're trying to minimize mass. So that particular element gets removed. Then it's going to make a whole bunch of decisions like that. It's going to remove a decent amount of material after the first run. Then it's going to rerun the simulation, and it's going to look for areas of very high stress, areas of low stress, and if there are areas of really high stress, it's going to do some things to add material back in to make that stress lower. And if there's still areas with really low stress, it's going to remove more material yet. So this is definitely one of those situations where it's an iterative operation. We may have to go through 100 simulations, we may have to go through 1,000 simulations to get there. My point is, if you make your mesh really fine, this is going to take a really, really long time to solve. So I just previously did a simulation, a topology optimization simulation. It was going to take about 24 hours because I set a really fine mesh. So I decided that was probably too fine, and we backed it off a little bit, and we made it a little bit more coarse, and it took a lot less time. So let's choose something down here, more on the coarse side than on the fine side, especially because this is just a learning process. So let's do that, and we'll push the green check mark. Okay, there's our mesh. That's probably still plenty fine. And you know what? I think I might want to, for the sake of a demonstration, I think I might want to go and make this all the way coarse. And that looks very similar to me. It looks like it's still going to be way more than fine. So that looks good. We are ready to run this thing. And I'm going to pause the video and come back when this is done running, because this is most likely a very long situation. So we'll be back in a second. I'm going to resume the video for just a second to talk about the progress bar. So when you run this, you're going to see this progress bar come up, and it's kind of fun to be able to watch the simulation unfold. You'll see that I'm already on iteration number 6. It just changed to number 6. So what that means is we can start to see a convergence plot. So I'm going to click this button and look at what's going on. So we can look at two things. We can look at our goal, which is to minimize the mass. So we can see what that looks like by double clicking on this little squiggly graph thing. You'll get a graph that looks like this. So what it's doing is it started out with a mass of this much, 4.6 times 10 to the negative 4th kilograms, and it's already been able to remove enough material to get it down to 3.4, which, I mean, that's a very small amount of mass because we're working with a small beam, a small low density balsa wood. But you can imagine we've already cut 20-25% of the mass off of this beam just by running a few simulations for a few minutes. So that's pretty powerful tool. The other thing we can look at is the stress. So this would be the maximum stress seen in the beam. And this is the kind of plot we're getting here. So this is the one that'll go up and down some, and sometimes you'll get that with your mass minimization goal too. But as the iterations keep piling on, it's going to try to get us towards that blue line, because if we get towards the blue line, that's the maximum amount of stress allowed. That also usually leads to the minimum mass too. So we'll see how this unfolds as it keeps going. And we're back. The simulation has finished, and as you can see, we have something that looks pretty ugly. And that's pretty normal for a topology optimization simulation. So if I'm looking around here, what I see is a big gap in the middle, obviously that huge hole in this midsection. I see over here, it looks like it's kind of rounded off these edges. which makes a ton of sense, right? All of that material is just wasted extra material. We would not need that one bit. It doesn't help at all. So that certainly can be deleted. Then I see some of this material looks like it's been removed. So some of that thickness, now that's going to be something really hard to recreate. Because if you're thinking about how will this eventually be manufactured, it's probably going to be cut with either a laser cutter or maybe a CNC router, something along those lines. If it's made out of balsa wood, if it's made out of aluminum or something, it's probably still CNC routed, maybe laser cut. Hard to know. Either way, this sort of stuff, and if we flip it over and look at the underside, all of this sort of missing stuff is going to be extremely difficult. We can probably get these middle sections, we can probably get that mass removed, but not in a 3D way, probably in a 2D, cutting out some holes, cutting out some cutouts. That's probably about all we're going to be able to accomplish. So the point is, a topology optimization study probably is not going to give you a final design. It's probably going to give you some ideas for a final design. So I would take this, go back to the drawing board, restart my model, and the first thing I would do is round this off for sure. Round that off, maybe make it semicircular here at the end. Maybe add some cutouts in between here where the simulation shows we can remove some material. I'm probably going to ignore stuff like this and just leave that as solid for now. But I think what we could do is we could probably remove a significant chunk in the middle of this beam and still be okay. Underside, yeah, not a lot to learn there. I would probably just keep looking at the top side. What I do want to point out though is look at how the simulation made this edge thinner on the bottom and made this edge thinner on the top. That's probably due to that reaction torque and how it was needed to be stronger on one side than the other. So that's interesting. So anyway, that's what you would do with this, is you would take this, draw inspiration from it, try to recreate it with something that looks a little bit more like traditionally manufactured. No one's going to want to show up with a drone arm that looks like this, even if we could make it. It would just look terrible. Look like somebody chewed it up. So that would be the next step. So let's just very quickly do that. We'll recreate this as best we can. I'm going to create one more new part. And real fast we'll recreate this. So I think that was 20 millimeters wide and 100 long, if I remember right. I think that was 10 millimeters from the edge. And this circle was a construction circle. And then we put some other mounting holes outside here, and those were 1 millimeter radius. And now let's pattern that. Around that circle. There we go. And let's attempt to do some of these cuts that we saw from the topology optimization simulation. So let's just continue to create more things in our sketch. One of the things that we noticed was this edge was rounded off, right? So we're going to do that first. We're going to round that off. Or that's an easy thing to round off later too. You know what? Let's create this box in the middle. It kind of created a box that looks something like this. And I don't know, let's make that 60 millimeters. And let's make it, oh, we already have that one defined somehow. We can make that, no, let's make that 4 millimeters. There we go. That looks good. Okay, let's go ahead and extrude that shape now. Let's do it everything the exact same way we did last time. I think we were at, what, a 4 millimeter thickness, if I remember right? Maybe that was only 3. That looks a little thick. Let's go to 3 millimeters. Okay, so there is our extruded shape. Let's also round those corners off. So let's get our fillet tool, and we're going to round these corners on this motor mount side. And let's be a little more aggressive than that. Let's say that that's a, I don't know, what's a 12 millimeter fillet look like? What was that thickness? Let's do 10. Semicircle. There we go. Perfect. Okay. Let's do one more thing to try to help ourselves out. These sharp corners are going to be really bad stress concentrators. So let's help ourselves out. Let's make these like maybe a 1 millimeter radius. Let's go for 1.5 millimeter radius. Just kind of smooth these corners out, all 4 of these sides. That will help reduce our stress concentrations in those corners, and we'll be able to get away with cutting out a bigger rectangle. Okay, there we go. So that beam is about 50% or maybe a little bit less in weight than our original beam. And let's run a quick simulation and let's just see if it does just as well. Okay, static simulation looks good. We'll do our fixed geometry, same as we have always been doing, over here on this side. Let's add our forces. And those were 1 Newton total. And now we have to give it a direction, and let's choose this direction. So good, it looks like they're all pointed down in the direction we wanted. Push OK. And now we have to add our external torques from our reactions. And we had been doing 0.05 Newton meters. And there it is on that one. We'll do that to the other 3 just the same. Oops, clicked on the wrong thing. There we go. Inside face only. And last one. Okay, all of our loads are applied. Let's create a decent mesh, because this won't take too long to run just one time. So let's make a nice mesh. Mesh is created, and let's run the study. Oh, we forgot to define the material. So let's go back up here and define our material. We'll make that the same as last time, the balsa wood. So we can close steel, go down into the woods, choose balsa wood, apply and close, and now we should be able to run the study. Did I miss something? Oh, if you don't define the material right away, you have to define it twice for some reason, one in each area. So apply it in both areas. If you want, you could have gone back to the model and applied it in that tab, and then it would have brought the whole thing over. But this is fine too. Okay, run the study. Okay, so it's giving me a new message this time. We haven't seen this before. Excessive displacements were calculated in this model. If your system is properly restrained, consider using the large displacement option to improve the accuracy of the calculations. Otherwise, continue with current settings and review the causes of these displacement. So we're going to click no for now. Okay, so let's see what we get here. And remember last time we went and changed the options inside this legend to make it a little bit easier for our brains to interpret that. So you could do that again. We've got 20 megapascals as our yield strength, and it looks like we're at about 9 right now. So we're still much lower than we could be, and most likely the reason that our topology simulation said that we were right where we needed to be, but we're not, is because we didn't make this any thinner. We didn't cut out any of that material here or along these arms, and I think that's where the high stress areas were. So what we could do is we could try to make this a little bit longer. Maybe that would cut some weight, maybe that increases our strength. We don't really want the stress to increase, but we do want our weight to go down. The other thing we could try is just overall making the beam a little bit thinner too, and see where that leads us. So anyway, that's how you use a topology optimization. Very handy tool. We were very quickly able to reduce our stress by reduce our mass by over 50%. So very, very powerful tool.